Hello everyone, hope you're doing well. So today we have this really cool question in which we're going to be discussing divisibility and congruence modulo, and maybe like the intersection of these two things to solve a relatively interesting question, So yeah, let's see how this goes. This is problem number 2 from the INMO in 2013, Indian National Math Olympiad. The IUQM just concluded, so might as well discuss some INMO problems, right? And in this video, we're going to be looking at congruence modulo in reducing equations, basically reducing modern essentially. And then divisibility techniques is probably going to be the highlight of this video. It's going to be like really interesting to see. And after that, we have certain book sessions for National Math Olympiads, and at the end, a similar but challenging problem. Okay, so this is what they've given us. So our goal is to find all m comma n belong to natural numbers such that it satisfies this given equation, this given like Diophantine equation, and it's also given that p is a prime. Okay, p is prime. Let me just maybe specify that p is a prime, and also like p is greater than equal to 5. The second condition is kind of redundant, but okay, anyways, does not really matter. But yeah, essentially p is prime. That's what we want to know. Then the exact question it is given that p is greater than equal to 5, but as we progress, you'll actually see that no solution exists for any smaller primes. But okay, so when you see this problem, what really can click to your mind? Maybe like reducing mod n's, or that might just immediately click to your mind. But there's actually like probably easier techniques to do this. So let's just maybe discuss a little bit about that. So m times 4m squared plus m plus 12 is equal to 3 times p raised to the power n minus 3. I can write this as 4m cubed plus m squared plus 12m plus 3 is equal to 3 times p raised to the power n. And believe it or not, the left hand side is actually factorizable. If I take m squared common, I get 4m plus 1. If I take 3 common, I get 4m plus 1 is equal to 3 times p raised to the power n. And now I get m squared plus 3 times 4m plus 1 is equal to 3 times p raised to the power n. Up till this point, I've done nothing but expand and factorize, right? As simple as that. So now we have this really beautiful equation, this really beautiful result that sum of two quantities is actually 3 times a perfect power of a prime. Quite interesting, isn't it? So essentially 3 divides m squared plus 3 times 4m plus 1. Right? That makes sense. So therefore 3 divides m squared plus 3 or 3 divides 4m plus 1. Right? So maybe let's just analyze both cases a little bit. So if 3 divides 4m plus 1, so 3 divides 3m plus m plus 1. So m plus 1 is congruent to 0 mod 3. Or in other words, m is congruent to minus 1 mod 3. So m is essentially congruent to 2 mod 3. And you can write m is equal to 3k plus 2. That's great. But if you look at this case, m squared plus 3 is congruent to 0 mod 3. And 3 is congruent to 0 mod 3. So essentially m squared is congruent to 0 mod 3. And if m squared is divisible by 3, then m has to be divisible by 3. M is 0 mod 3. So therefore m is 3k. So we can reduce into two cases. Case 1. M can be either 3k plus 2, which is 2 mod 3, and case 2 would be m is 3k, which is 0 mod 3. That's great. So we are going to reduce the question to this, right? 4m plus 1 times m squared plus 3 is equal to 3 times p raised to the power n. That's great. So if I just maybe substitute m is equal to 3k plus 2 over here, let's just see what we get, right? 3k plus 2 whole squared plus 3 is equal to 3 times p raised to the power n. And when you really simplify this, you get something like this, okay? 4k plus 3 times 9k squared plus 12k plus 7 is equal to p raised to the power n. So now essentially what we can figure out over here is that 4k plus 3 will be some p raised to the power a. And right, 9k squared plus 12k plus 7 will be p raised to the power b. So essentially, can I actually say that p raised to the power a divides p raised to the power b? Right? If let's say a is less than equal to b, right? So for example, if p raised to the power a is, let's say, p cube, and p raised to the power b is p raised to the power 5. So obviously p raised to the power a divides p raised to the power b, right? Because p raised to the power b divided p raised to the power a is p squared. Right? B minus a, 5 minus 3 is 2. So yeah, essentially the smaller quantity among these two will divide the larger quantity. So we can either have 4k plus 3, which divides 9k square plus 12k plus 7, or we can have 9k squared plus 12k plus 7 divides 4k plus 3, depending upon who is larger, and that essentially depends on the values of k, right? Now let's just analyze both of these things. Let's just consider 4k plus 3 versus 9k squared plus 12k plus 7, and maybe let's just take some corresponding values of k, k0, k1, k2, k3, and so on and so forth. If I plug in k is equal to 0, I get 3, here I'll get 7. If I plug in k is equal to 1, I'll get 7, and here I'll get 28, right? 12, 19, and 9, 28. If I put k is equal to 2, I'll get 11, and if I put k is equal to 2 over here, I'll get 9 times 4, 36, plus 12 to 24, plus 7, which is 36, 16, around 67, right? But my point is, you know, you get 3, you get 7, here you get 7, you get 28, you get 11, you get 67. So essentially, by induction also, I can actually prove that 4k plus 3 will always be less than this thing, 9k squared plus 12k plus 7, right? And this is essentially very simple. You know, you can kind of like you can just like plug in certain values of k and actually see that both of these are actually increasing functions. That's very clear. But this is increasing function. But however, you know, 4k plus is always going to be less than this quantity, and that is kind of like we just checked that by inspection. So therefore, 4k plus 3 needs to divide 9k squared plus 12k plus 7. A lot of people, they might have just like said that 4k plus 3 is smaller just in the fact that it is linear. That does not always hold true. Okay, don't fall into the assumption that because it's linear and this one is quadratic, linear will always be smaller. No, we'll actually see in the second case that does not hold true. Quite interesting. Okay, so here comes the divisibility, right? We're talking about divisibility. Okay, let's see how we can proceed with this. Right, so 4k plus 3 needs to divide this. So what can I do? Maybe. So for example, okay, let me put it this way. So for example, if x divides p, then can x divide 4p? Of course it will, right? Of course it will. For example, 9 divides 36. Will 9 divide 36 times 4? Of course it will. There's no doubt about that, right? So essentially, 4k plus 3 divides 9k squared plus 12k plus 7. Now, if I just multiply this entire thing by 4, it will 4k plus 3 will still divide that, right? 28k squared plus 48k plus 28. Why I did that was essentially now I can write this as, so this divides 4k plus 3 times 9k plus 5 plus k plus 13. So essentially now 4k plus 3 divides k plus 13, and again just the same strategy, really multiply by 4. You know, I'll get 4k plus 3 plus 49. 4k plus 52, I just split it like this. So essentially 4k plus 3 divides 49. And what are the numbers that divide 49? The natural numbers. It's only like 1, 7 and 49, right? So 4k plus 3 can either be 1, 7, 49. If 4k plus 3 is equal to 1, you know, you'll get k as some negative number, and k is obviously a natural number. 4k plus 3, if you consider it to be 49, k won't, again, it won't be an integer really for this case. So the only thing that remains is 4k plus 3 is equal to 7, so you get k is equal to 1. And when I plug in k is equal to 1, and m was what, 3k plus 2, right? So m is equal to 5. But when I plug m is equal to 5 into our equation, 4m plus 1 times m squared plus 3 is equal to 3 times p to the power n, right? So this becomes 21 times 28 is equal to 3 times p to the power n, 7. So p to the power n is actually 196. And you see, what is 196? It's actually 14 squared. But 14 is not a prime, it's a composite number. That's why I kind of specified in the question that p is prime. So this really has no solution. No prime raised to power n is ever 196. So no solution for case 1. That is m is equal to 3k plus 2. So m is equal to 2 mod 3 has no solutions. Right? That makes sense, I hope. So moving on to this case 2, right? What is case 2? M is 0 mod 3. Essentially, m is 3k. And when I plug that into the given equation, so we had this, right? We had 4k plus 3 times 9k squared. Wait a second. Yeah. Okay, great. So yeah, for this case, we have m is equal to 3k, right? And we can just reduce this as 4m plus 1, and m squared plus 3 is equal to 3 times p to the power n. And then you just plug in m is equal to 3k into this, you will get nothing but 12k plus 1 times, just plug in 3k over here to get 9k squared plus 3 is equal to 3 times p to the power n. And again, just divide by 3 on both sides. You will get 3k squared plus 1 is equal to p raised power n. Now, no, again here, if you remember from case 1, here also either 12k plus 1 divides 3k squared plus 1, or 3k squared plus 1 divides 12k plus 1. And again, really, you just need to formulate, maybe just take some values of k and check, right? So 12k plus 1 versus 3k squared plus 1. Let's consider for k is equal to 0, k1, k2, k3, k4, and k5. Let's just consider that. If I plug in k is equal to 0, I get 1. And here also, coincidentally, I'll get 1. If I plug in k is equal to 1, I'll get 13, but here I'll get 4. Quite interesting. And k is a natural number, so you don't really need to consider 0, but just for like showing purposes, I'm just doing that. If I plug k is equal to 2, I'll get 25. If I plug in k is equal to 2, I'll get 13. Okay, interesting. So here, actually, the quadratic term is kind of smaller. Now, let's just see if it's always smaller. Okay, if I plug in k is equal to 3, I'll get 37, right? I'll get 28. So if you see, the gap is kind of decreasing, right? Here the gap was like 9. Here the gap was like 12. Here the gap is again decreased to 9. Maybe if I plug in 4 over here, I'll get 49. If I plug in 4 over here, I also get 49. Oh, the gap is closed. Wow. If I plug in 5 over here, I'll get 61. If I plug in 5 over here, what will I get? 76, right? 25 is 75 plus 176. So if you actually kind of like go this further, you'll actually see that for k is greater than equal to 4, for k is greater than equal to 4, 3k squared plus 1 is greater. So this is greater than 12k plus 1. So essentially, 12k plus 1 divides 3k squared plus 1 for k greater than equal to 4. And what is remaining is essentially k1, 2, 3, which you can just take by hand at the end. But yeah, just ignoring that, 12k plus 1 divides 3k squared plus 1. Again, now if I just multiply, like we've done before we had multiplied by 4, let me just multiply 48 over here, right? Times 48. So I'll get 144k squared plus 48. Why? Because now this is easy to deal with. I can just write this as 12k plus 1, 12k minus 1, and plus 49. Right? I can write it like this. This is transformed to this essentially. So essentially, 12k plus 1 divides 49. You can just directly simplify this. So again, what are the divisors of 49? 1, 7, 49. Right? So 12k plus 1 is again 1, 7, or 49. Again, just to reiterate, k cannot be 0. It's a natural number. 12k plus 1 is equal to 7. Does not let k be an integer. So the only remaining possibility is 12k plus 1 is 49. Or in other words, k is equal to 4. So if k is equal to 4, what is m? M is 3k, and you'll get m is equal to 12. If you put it back into the original equation, you will actually, let's just see what we get, right? We had 12k plus 1 times 3k squared plus 1 is equal to p raised power n. If I put k is equal to 4 over here, I get 49 times 49 is equal to p raised power n. So p raised power n is 49 squared is 7 raised power 4. So p7 n 4. That's really great actually, because m is equal to 12, p is equal to 7, and n is equal to 4 is a valid solution. Right? That's great. Now let's just check the remaining things. Like this was obviously for k greater than or equal to 4. So essentially what is left is k is 1, 2, and 3. Like I said before, k is a natural number. Cannot be 0. Okay, great. So what did we have? We had 12k plus 1 times 3k squared plus 1 is p raised power n. If I plug in k is equal to 1, I'll get 13 times 3 plus 1, 4 is p raised power n. Obviously, 52 cannot be a power of a prime. If I plug in k is equal to 2, I'll get 25 times 13, which is again can never be p raised power n. If I plug in k is equal to 3, I'll get 37 times 28. Will that ever be p raised power n? Never, right? Because this is prime, this is not, can never be p raised power n. So no solutions for k is 1, 2, 3. So the only solution, so one and only solution is n4, m12, and p7. So that was a really interesting question actually, and the takeaway is kind of the divisibility things that we did over there, and yeah, this is really fun to do. So and yeah, not like really lot of complicated questions, lot of really complicated concepts involved there, I would say, but the simple things made tricky, and that's the INMO for you. So okay, yeah, let's move forward. Right, so after that we have some book sessions for National Math Olympiads. We have Elementary Number Theory by David Burton, Principles and Techniques in Combinatorics, problem solving strategies by Arthur and Gell, functional equations by Venkatachala, problems in plane geometry by Sharigan, elementary number theory by Sierpinski, graph theory by Harari, and combinatorics by Brualdi. Okay, so at the end we have a similar but challenging problem, and the goal is to let p be a prime and x, y, z are integers, so that this particular equation has the only solution x is y, z is 0. So x cube plus py cube plus p squared z cube is equal to 0. So this has only solution x equals to y is equal to z equals to 0. So we have to prove that again using divisibility techniques. And there are other ways also. Maybe you can try infinite descent also, Vieta root jumping, if you've heard of that. Quite an interesting problem solving technique. But yeah, divisibility is more than sufficient to solve this. And yeah, as usual, if you make any progress on it or if you're able to solve it, let me in the comment section. And until then, I'll see you in the next video. Thank you very much. Bye-bye.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit Cheenta.com.